What is going on, guys? Welcome back. In this video today we're going to learn how to train a convolutional neural network to classify different classes of images like dogs, frogs, trucks, ships, and so on using PyTorch. So let us get right into it. Alright, so we're going to train a convolutional neural network in PyTorch today, which is going to be able to classify 10 different types of images, the 10 classes present in the Cypher10 dataset, which we're going to use for training, and it includes vehicles and animals, so the classes are dog, cat, horse, ship, truck, car, and so on. And we're going to go through the full process. We're going to load the data, we're going to have training and testing data, we're going to train the model, and we're going to evaluate the model. Now, the first thing we want to do is we want to install the packages needed for this video today. These are 4 packages, so we're going to do pip or pip3 install numpy, pillow, torch, and torch vision. So these are the 4 packages. I already have them installed, so I'm not going to run the command again. And then what we want to do is we want to open up a Jupyter notebook. I recommend working with a Jupyter notebook, not with an ordinary Python file, because in this way you can rerun individual cells. You don't have to constantly train the model if you make a small mistake. So I recommend working in a notebook. We're going to start with the imports. First of all, import numpy snp. From pillow, we want to import image. Then we want to import torch. We want to import torch.nn as an n. We want to import torch.nn.functional as f. And we want to import torch.optim as optimization or as optim. And then we also want to import torch vision. We want to import torch vision.transforms as transforms, and I think actually that's it. So these are the imports, and then we're going to start by defining transformations that we want to apply to any incoming data before it comes into the network. So when we get image data, it's going to be between 0 and 255. These are the RGB values. We want to scale them to be between -1 and 1, and we want them to have we want them to be tensors. So we're going to start by saying that our transform is going to be equal to transforms.compose. So we're going to compose, we're going to combine a couple of transforms. The first one is going to be transforms.toTensor. This turns it into a tensor, and it also already normalizes it to be between 0 and 1. So 0 and 255 is scaled down to 0 and 1, to a range of 0 and 1. And what we need to do now to get the values between -1 and 1 is we need to normalize with a mean of 0.5 and a standard deviation of 0.5, because that way we subtract 0.5 and we also divide by 0.5, which leads to first of all getting to 0.5, and then or first of all getting between -0.5 and 0.5, and then we basically multiply by 2 and we get -1 and 1. So we say transforms. And we do that, by the way, to speed up convergence. This is just a better range to work with. So we do transforms, normalize, and we pass 0.5 for each channel. And for the standard deviation, 0.5 for each channel as well. All right, so that is our transform. This is what we're going to do with the data before we feed it into the neural network. And now we need to get the train data by saying torch vision datasets Cypher10. You can also go with Cypher100 if you want to use 100 different classes of images. We're going to define the directory to be ./data, so just a data directory here, current directory, and then a data directory. We want to load the train data, so we're going to say train equals true. We want to apply a transform, so the transform is going to be equal to transform. We want to download the data, so download equals true, and actually that's it. Then we want to copy that and change that to test data. The only difference here is that we're going to set train to false, and then we want to create data loaders that load the data from here. So we want to say train loader is going to be equal to torch utils data loader, actually with a capital D and L, so the class. Here we pass our train data, we pass a batch size of 32, we want to shuffle the data, so we set that to true, and we want to use 2 workers to do that in parallel, just to speed it up a little bit, and test loader is going to be the same thing, but with test data, of course. So this is now our data. This already downloads the Cypher 10 dataset. We can keep coding while this is happening. The next thing that we want to do is we want to take a look at the data so that we can see how it's structured, what the shape is. For that, we're going to say image and label is going to be equal to train data 0. And the image is going to look like this, or let's go and say image shape, or actually image size. We can see that the size here, or the shape, is 3, 32, 32. So we have 3 channels, RGB, and 32 times 32 pixels. That is how an image looks in our dataset. Now, this is going to be our input shape, and then we also need to know what the output is. The output is going to be one of the 10 classes, and we need to actually code in the labels here. So I'm going to say class names is going to be equal to the following list. We're going to have plane, we're going to have car, we're going to have bird, we're going to have cat, we're going to have deer, dog, frog, horse, ship, and truck. So these are the 10 classes. These are the labels for the 10 classes because our network is going to produce a number between 0 and 9 representing the individual classes. 0 is going to be a plane, 1 is going to be a car, and so on. 9 is going to be a truck. These are the class names. All right, so let's get to the interesting part, our neural network. For this, I'm going to create a class neural net, which is going to extend from nn.module. This is just the base class from PyTorch for a neural network. And the important thing is here now we need to have 2 methods. First of all, the init method, which is the constructor, takes self here as an argument. This is going to define the structure. And the second thing is the forward function, which is going to define the feed forward logic. So we do that. We say super init first so that we can call the init method of the parent class. And then we define our architecture. The first thing we want to have is a convolutional layer. So we're going to say self conv1, the first convolutional layer, is going to be equal to nn conv2d, convolution 2d. And now we need to specify what we want to have here. Now we want to start with a shape of 32 times 32 pixels. This is our input. And what we want to do then is we want to define that we want to have 3 input channels. We want to have a certain number of output channels, or as we call it in convolutional neural networks, feature maps. So these are the results of applying the kernel or the filter. I don't want to go too deep into the theory of neural networks here. If you want to have a detailed explanation of convolutional neural networks, let me know in the comment section down below. But basically, we have a kernel or a filter that has a certain size. We're going to use now a 5x5 kernel. This is like a thing that moves over the image and extracts features basically by calculating a dot product. Now, what the filter is, in the beginning, it's going to be some random stuff. Over time, it's trained. So the filter itself or the kernel itself is being trained during the process, during the training process. But basically, we have our image, 32 times 32 pixels. We have a 5 times 5 pixel kernel that moves across the image, calculates a dot product, and creates feature maps. So we have 3 input channels. This is defined by the shape of our data. And we want to produce a certain number of feature maps. Now let's just go with 12 in this case. And our kernel will have 5 times 5 as a size. So in this case, we have 5 times 5 as a kernel moving across the image and producing 12 feature maps as a result. Now, what happens here is that we get a new shape. So the calculation here is that we have our input size minus the kernel size. So we have 32 minus 5, which leads to 27. We floor that if necessary, or actually we divide that first of all. So we have 32 minus 5 divided by the stride. So how much our kernel moves while going. So if it just moves 1 pixel, it's a stride of 1. If it moves 2 pixels, it's a stride of 2. In our case, we're going to use the default of 1. So we have a division by 1, which is 27 divided by 1, which is 27. And to that now we add plus 1, or we add 1. which leaves us with a new shape of 28. So our new shape after the convolutional layer is 12 channels with 28 times 28 pixels. That is, or 12 feature maps, you could say. This is now our new shape. After this, what we want to do is we want to apply a max pooling layer. So we're going to say pool is going to be equal to neural network dot max pool 2D, and this basically turns, depending on the size, we're going to use 2 times 2. This is going to take 2 times 2 pixels, so 2 times 2 area, 4 pixels, and it's going to create 1 pixel out of that. So it's going to basically extract the most important information. And this is going to lead to a division by 2 when it comes to our shape. So this is going to leave us now with 12 times 14 times 14 as a shape. Then what we're going to do is we're going to have a second convolutional layer, which is going to be nnconv2d. This is going to take now 12 input channels, obviously. We're going to produce 24 as an output, so we're going to create from the 12 feature maps, again, another abstraction, 24 feature maps, again with a 5 times 5 kernel, leading, of course, again to the same calculation. We have the size 14 minus 5 divided by 1. This is going to be 9, plus 1 is going to be 10. So now we have, actually, our new shape is 24, 10, 10. Now we're going to apply another max pooling operation here, but we don't need to define the layer again, so we're just going to reuse this one. So actually what happens here is we have this again, 24, 5, 5. I'm going to define, or we are going to define that this happens in the forward logic. We don't need to do it here by creating an extra layer. So what I'm going to do is I'm going to say conv1 pool, conv2 pool, which I don't have to specify here because I already have the layer. And then we're going to move to fully connected layers, so to to dense layers in TensorFlow language. So self.fully connected one is going to be equal to a linear layer, which is again just a dense layer or a fully connected layer. And since we have 24 times 5 times 5, what we want to do after this layer is we actually want to flatten all of this. So the shape is going to be 24 times 5 times 5. And because of that, I'm going to get 24 times 5 times 5 as an input here. And I want to output 120 neurons. Then I want to have another fully connected layer that takes these 120 neurons and outputs 84 neurons, for example. Self.fully connected 3 is then going to take these 84 neurons, and now the important thing is we need to have 10 output neurons. This is important. Everything in between you can play around with. Now you need to have 3 input channels, obviously, but you can choose a different number of feature maps, you can choose a different kernel size, a different max pooling size, you can choose different channels here, you can choose a different number of neurons in here. Now, of course, you need to keep everything compatible, so you cannot just choose any number here. This number needs to be compatible with the shape that you get here. But in between, you can do anything. So you can go with 28 here. You can use different numbers. It doesn't really matter. You can go with 140 here and with 92 here. It doesn't matter. But at the end, you need to have 10. You can play around with different parameters and layers. You can add more layers. You can change the numbers here. But you need to get 3 input channels and 10 output neurons, which are the 10 classes, the probabilities for the 10 classes. That is our model itself. Now, the forward method here is going to take self and x as a parameter. So x is going to be the input, and the forward function just applies these layers onto the input. So first of all, what happens is we take our input value and we feed it through the first convolutional layer. So conv1 applied to x. The result of that is then fed through a ReLU function, rectify linear unit. This is basically just 0 if the input is 0 or less than 0. And it's the input if the input is above 0. So this is basically, if we plot this as a coordinate system, the function takes an input and produces 0 most of the time, and then it's just a linear function. That's the ReLU function, the ReLU activation function, which is a very efficient and useful function. So we do f.ReLU applied onto the output of the convolutional layer to break linearity here. This is the important thing about an activation function. It breaks linearity. And then this result is fed through a pooling layer. So self.pool applied onto f.ReLU applied onto self.convolutional1 on the input. The next thing we do is we do the same thing again, self.pool, f.value, self.conv2x. And then we just apply a flatten operation. We say x is equal to torch.flatten x1. And then we say x is equal to applying ReLU onto the output of the fully connected layer 1. So we take the fully connected layer, feed the input through it, apply a ReLU function. We do the same thing with fully connected 2. And then in the end, we get self.fully connected 3 applied onto x. Now, of course, what this means is we just feed the input data. We apply the kernels or filters onto the data. We apply a ReLU function and so on. And everything that these layers do, the kernels and here also the weights and biases, all of this is going to be trained. All of this is random in the beginning or initialized in a certain way, in a certain random way, and then it is trained into the neural network by showing examples. So we return x, and that is basically our neural network structure and logic. Now, to actually train this, we're going to define, first of all, the network itself. The net is going to be neural net instance here, and the loss function that we're going to use for this is categorical cross entropy. So we're going to use nn cross entropy loss here as a function, and we're going to say that the optimizer is going to be a stochastic gradient descent. So optim is going to be, or optimizer is going to be optim.sgd. We're going to train the parameters of our network. So this is what we're applying this optimization on with a learning rate of 0.001, and we're going to use momentum optimization. We're going to pass 0.9 here as a parameter for that. So this is now everything defined. To actually train this, we need to now go through some epochs. So I'm going to say for epoch in range 30. What I'm going to do is I'm going to say training epoch. Let's actually use an f string here. Training epoch like this. And then we're going to say that the running loss, so we're going to add up the losses for the individual instances here. So we're going to say running loss is 0.0 in the beginning, and then for I data in enumerate train loader. What we're going to do here is we're going to get the batches from the train loader, and we're going to say that the inputs and the labels is going to be equal to data. And this is basically what we get from the train loader, so the individual batches. And then we say optimizer dot zero grad, so we reset the gradients. We set all of the gradients to none. And then what we do is we say the outputs of the neural network is whatever the network produces given the input. So we take the inputs from the data, we feed them through the network, we get some output. In the beginning, it's going to be completely random and wrong. And then we calculate the loss. So we want to know, compared to the actual output that we desired, compared to the labels, what are our outputs. So we say loss equals loss function, and we feed in here the outputs that we got and the actual desired outputs, so labels. And then what we do is we back propagate the loss. So we call backward loss.backward to do the gradient computation, and then we take a step using our optimizer. So all of this is implemented already in PyTorch. We don't need to implement backpropagation itself, but what we do is we get the output of our network, we calculate the loss, we propagate the error back through the network to compute the gradients, and we take a small step, depending on the learning rate, into the correct direction for each parameter that we have. And in the end, what we do is we say running loss plus equals loss.item. And at the end of every epoch, we want to print the loss. So the loss is going to be running loss divided by the length of the train loader. So divided by the data, we want to have an average here, rounded up to 4 decimal places. All right. So that is our training loop. I can run this now, and we're going to see what happens. It trains epoch 0. It's going to take some time, and it's going to show us, hopefully my recording can handle this, and it's going to show us the loss. Now I think, did I mess up something? Because this seems to be, oh yeah, I messed up something because we need to say plus equals, not equals plus. Because this seemed to be a little bit too low for a loss, so let me restart this again, run all of this again, and then we should start the training loop. Training epoch 0, we should have a loss in the beginning that's a little bit higher than 0 point something, so it should be something, yeah, around 2. 2.1, training epoch 1, and so on. And the thing that you're hoping for here is to see a convergence. You want to see that the loss goes down, so it's 2, then 1.6, and then 1.4, 1.3, and so on, up until a certain point where it's going to not show a lot of progress. So hopefully something around 0 point something, 0.4, 0.3. And you can keep going. You can use more epochs. You can go for 40 epochs, 50 epochs, whatever. But you want to see that the loss is decreasing. If the loss is staying the same or even diverging, even going up and down, you know, not converging to a value, then probably something's wrong with your network, or you're training it for too long. You have a too high learning rate or something like that. But if you have something like this, where it's constantly decreasing a little bit and converging to some small loss, then this is what you want to have. Now, while this is training, I want to keep coding, because afterwards, once this is trained, we're going to export our model parameters so that we don't have to retrain the model when we want to use it again. So assuming that this is already trained, we're going to do torch save net, and we're going to get the state dictionary of that neural network, so the parameters, and we're going to export them to trained net.pth. That is going to be our code here. And then in order to load that in another script, now we don't need to do it here, but we can do it here. We need to create a neural net instance. So we need to define this architecture as well, again, because we're not exporting the whole model. We're just exporting the weights, so the parameters, or the weights and biases, and the kernels. And the network needs to be defined as a structure, and then we can load the state dictionary. So we can say net load state dictionary. And as a parameter here, we're going to pass torch load trained net.pth, like this. Yeah. And then we can move on with the evaluation part. So I can actually run this now. Once this is done training, you can see it's still decreasing the loss. Once this is done training, we can save all that. And then we can evaluate it on the test data. How do we do that? We do that by saying correct equals 0. Total equals 0, because what we want is we want to have an accuracy metric. So how many of the total, actually with an A here, how many of the total instances were classified correctly. And for this, what we do is we set the network to evaluation mode, which, because the network works differently during evaluation and during training, depending on what you do in a network, certain parts of the network will behave differently during evaluation inference. And we also say with torch.noGrad to not do any gradient computations. Actually, now I ran this. This is not good. But we're not doing any gradient computations because we're not training the model. We're just feeding input forward through the network and getting a result. So you can see it's still decreasing here, so it might make sense to run it for more epochs, maybe for 50 or something like that. But I'm going to stop doing this here now at 30 epochs. So with torch noGrad, disabling the gradient computation, we say for data in test loader. So now we're getting our test data. What we do is we get images, and labels is going to be equal to data again. And then we say the outputs is going to be equal to our neural network applied on the images, so on the 32 images, or on the 32 image batches. And then we want to see what the prediction is, because our network outputs 10 values and we want to have a label. So we want to say that the prediction here is torch.max of the outputs, and we want to have the one instance, or the one thing that is that has the highest activation, which is going to be our label. And we want to say total plus equals labels dot size 0, so 32 in our case. 32 instances that we classified, and the correct ones are going to be plus equals where predicted is equal to labels, and we're going to sum them up and get the item. So basically, we're counting how many of them have a correct classification, how many of them were classified in general. So 32 is going to be the total for each batch, and correct is going to be how many of them are being classified correctly. And the accuracy is obviously going to be in the end just 100 times correct divided by total. And I want to print that as a metric here. Accuracy is going to be equal to accuracy %. So I can run this now, and this gives us, in this case, 68.99%. It will probably be better if you continue training this here, if you have more epochs, but this is already quite good if you consider that we have 10 different classes. So this would be not so good if you just had cat or dog, but considering that we have 10 different classes, this is quite good, and we can actually see if it works on example images. So I have 2 example images here, example 1 and example 2, which are 2 images which are not from the data set. I got them from the internet. And we can feed them in now, and they also don't have 32 times 32 pixels, so we need to actually resize them. And this is what we're going to do now in the final cell. We're going to say from pillow import image, or actually we did that. I think we did that in the beginning. Yeah, we already imported image, so we don't need to do that. But we need to define a new transform. And the new transform is going to be the same as the old transform, but we're going to have an extra step. So we're going to say transforms compose. And we're going to do the same thing of transforms dot to tensor and transforms dot normalize, because we need to have the same input format. So again here 0.5, 0.5, 0.5, and again 0.5, 0.5, and 0.5. But we also need to add an additional operation here, transforms dot resize, and we want to resize everything that we get to 3. Or actually 3 is not necessary, to 32 times 32 pixels. So that is also what we need to do here, since our images are not going to always be of that format. Then we're going to define a function, a load image. This function is going to take an image path. And what we're going to do here is we're going to just say image equals image dot open image path. And then image is going to be whatever we get after applying our transform on the image. And then the image is going to add an additional, or we're going to add an additional dimension here by saying unsqueeze 0. The reason we do that is because we want to have a batch. So we want to have a batch dimension added onto this, because even if it's a single image, it has to be presented as a batch of one image, just for the shape to be compatible. And then we return the image here. And what we want to do then is we want to say the image paths that I have here, and now you can input all the images that you want. So in my case, it's example1.jpg and example2.jpg. And the images here are going to be, and if you have a folder full of images, you can do that here as well. But I'm going to say load image for image in image paths. Like this. And all we need to do now here is we need to do the evaluation. So we set the network again to evaluation mode. We say with torch dot no grad, so no gradient computations again for image in images. What we want to do is we want to get the output from the neural network applied onto the image, and we want to get the prediction. The predicted is equal to torch max. And then our output 1, and then we print that our prediction is going to be the class name of the prediction. So we get a number, but we want to have the item, the number value, and we want to feed it, we want to get the respective class name here. So when I run this, you can see I get prediction plain and prediction dog, which is accurate. This is a plain and this is a dog. So these images were classified correctly. They didn't have 32 times 32 pixels, so they were resized. And this is how you can do that. This is how you can use that model now to classify new images. And I think if it's not online already, I will soon upload a video where I show you how to deploy such a model onto an actual server. So either it's already on the channel or you're going to see that video in a couple of days here showing how to deploy such a machine learning model as an application on an actual server. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you very much for watching. See you in the next video and bye.